Welcome students to another video lecture with Mr. Kinnett. We're going over our last two sections of chapter 9, where we will finally jump into the world of systems of equations. And what a system of equations is it's not just one equation in a problem. It's going to be two equations or more that are connected together, and we're trying to find a solution that works for all of them. In this level of math, we're going to deal with just two equations. And when you have a system with two equations, you likely have two variables. So we're going to learn how to solve a system that has two variables now. In chapter 8, we just learned how to solve things with a single variable. So again, we're jumping into the next world. We're learning how to solve things with two variables. And I'm going to have you go ahead and pause here and copy down what you see. Okay, welcome back. So our essential question is, how can we solve systems of equations by graphing, substitution, or elimination? And what we're going to recognize in this lesson is that the answer to a system is the location where the two lines intersect on a coordinate plane. So that's why we like to start with the graphing method of teaching how to solve a system, because it gives you a good visual example of what we're looking for. We're looking for these two lines to intersect on the coordinate plane. Just like we learned in chapter 8 as well, at the end of this lesson, we'll have those special solutions show up. In chapter 8, we learned when variables were on both sides, sometimes you can end up with the answers of no solution and infinite solutions. And that's also possible in systems. So at the very end of this lesson, we'll go over how something would happen to have no solutions in a system, as well as infinite solutions in a system. So there are going to be three different ways to solve a system of linear equations. We can either do it through graphing, which again is not going to be the fastest method, but it's a good visual for you to see that we're looking for where two lines intersect. The next way we're going to learn is substitution, which works really well when there's already a variable by itself. And the last method is going to be the method I use the most, elimination. And I like it the most because it does always work. There's no scenario where it wouldn't work. It always works. So let's go ahead and start learning about our graphing ability of how to solve a system of linear equations. First thing you'll notice is there's not one equation in the example, there's two. And the two equations will normally be connected with this brace here. And that brace shows you that these two equations are together in the problem. So, like we learned in 9.5 in the slope-intercept form lesson, that is the fastest way to graph something. So I use the graphing method to solve systems when the y is already by itself, or it just seems easy to graph. So I tried to give a little bit harder example. Both equations don't have y by themselves, because I wanted to show you how you would do this method even if both y's were not already by themselves. So in this system, we have two equations, the first one and the second one. And you may notice this second equation already has y by itself. So I'm going to start with graphing that one on the coordinate plane. We use that skill of slope-intercept form to learn that there's a quick way to graph it. The slope is 1/2. The y-intercept is 1. So we plot our y-intercept, and then we graph our second ordered pair using the slope. Make sure when you do these lines, you are using a straight edge. It's going to be really important. If you don't use a straight edge, it's likely not going to show us where the answer is. And that's because you may have a little zigzag or curve. And that will cause our problem to be a little harder because we won't visually be able to see where the two lines intersect. So again, use a straight edge. Another skill is when I put more than one line on a coordinate plane, I have learned it's smart to label that line so I know which line is which. So I label it either in the lower left or the upper right, whichever one keeps it out of the way. But I always label it, just like I've learned in science, to keep things organized and understood. So the first line, pretty simple to graph. Now we're going to graph the second one. And you may have noticed that the key to this is graphing each line separately. We're never trying to do both things at the same time. We're doing it one line at a time. The first equation in our system here didn't have y by itself. So if you need a reminder on how we're doing this, please check the 9.5 note. At the very end of that lesson, we learned how to get y by itself. It's pretty simple on this one. So now we're going to graph y equals negative 2x. And its slope is negative 2 over 1. And its y-intercept, oh, there is no number there. So that makes it easy. That means the y-intercept is the number 0. So we graph that ordered pair, 0, 0. And then we apply our slope. Once we have those two things there, we use a straight edge. Remember, can't stress that enough. And we connect all of these lines here. And the system of equations, the solution for this system of equations, is going to be in that location where the two lines intersect. It's right here. And unfortunately, Alex gave me a problem that ended up with a fractional answer. So this is a good example of where graphing is a hard method to use for solving systems. That kind of makes it look like it's a fractional answer. And it is possible that we can get fractional ordered pairs for our answers. So we are going to use another method on this to find exactly what that ordered pair will be. But the answer to the system is right there, the blue dot, the location where the two lines intersect. So I'm sorry that example didn't work out, but it did have an answer. We're just going to have to use another method to get its exact answer rather than hypothesizing where those lines are in respect to the coordinate plane. These steps will work great though, so don't give up on them. So let's jump on to our next method. Solving a system of equations using substitution. I like to use the substitution method when a variable is already by itself, or when I've noticed that there is one of the variables with a coefficient of 1. So we already have a variable that's by itself, this y here, and its coefficient is already the number 1 in front. I have devised a skill to keep this problem organized. I use this T-chart. And I use it because it's going to be important which equations we substitute into when. And I use this and it will help keep us a little organized. So step 1, solve for any variable. It doesn't matter which of the 4 variables you choose. You should solve for the one that is the easiest to solve for. In this problem, y is already by itself, and therefore it's easy to solve for. It's already been done. So we're going to list it first in the upper left. The next part is to substitute into the other equation. So we have to write the other equation down. The other equation is 4x plus 5y equals 11. Now, this method is called substitution. So can you think about what we're going to do with this y expression in this y location? What are we going to substitute into that y's location? What do we know y already equals? Yeah, we already know y equals this expression. I know it's not a number, it's an expression, but it still works. So we substitute it into there. We have 4x plus 5 parenthesis 3x minus 13 equals 11. And you notice now, there's no longer 2 variables in the problem. There's 1 variable in the problem. And since there's only 1 variable, we use our skills we learned back in chapter 8. You know it, good old Piam, to get x all by itself. So we have a distributive property. We're going to do 4x plus 15x minus, I got to do some math here. I need an x there. 5 times 13 is going to be 65 equals 11. Oh, my smartboard is messing with me. Then we have like terms to combine. So we're going to have 19x minus 65 equals 11. And now we just have to get x all by itself here. We're going to add 65 with our additive inverse. And we end up with, wonderfully, 76 equals 19x. And now we have to divide by that 19, or use its multiplicative inverse. And I know many of you didn't know this, but 19 times 4, yep, it turns out it's 76. So x equals 4. A lot of the time, students rejoice once they get the x value, forgetting that the location on the graph where these two lines intersect is an ordered pair. So since we already have the x value, we still have to go find the y value. And this is where the organization matters. We cannot substitute this value back into the same exact equation we started on, or we end up with some funny answers. We have to substitute this answer into this equation. So we have y equals 3x minus 13, and we're going to use the x value of 4. So we have y equals 3, let's see, minus 13. We put our 4 in there, and we follow the order of operations to get our y value. It turns out, once we do 3 times 4 minus 13, y equals -1. So the answer to this system of equations is the ordered pair 4, -1. This is the location on the graph where these two lines will intersect. Okay, I know my video lecture is getting long. I apologize, but we're going to move on to the most used one, and then we'll talk about no solution and infinite solutions in class. So I'm going to jump ahead here. Go ahead and copy down what you see. Pause here and copy down what you see. Welcome back. Okay, step 1. For elimination to work, you have to line up in each equation the like terms. So as we look at our system, right here, the y and the 4x are lined up, and the -3x and the 5y are lined up. Are those like terms, though? No. So we're going to commute this line so that we're going to rewrite it. We're going to not mess with the first line. It's going to stay the same. But the second line, we're going to commute around that addition sign and write it as 5y plus 4x equals 11 instead. Okay, now the next part of this elimination process is really similar to when we add fractions with unlike denominators. We had to make them have like denominators. So we're going to recycle that skill in this system problem. What we're going to try and do is create opposites so that when we add or subtract these equations together, one of the variables is going to get eliminated. Okay, so it doesn't matter whether you decide to get rid of the x values or the y values, you just have to focus on one of them. And for this problem, I've decided I'm going to focus on the x values. So we have -3x and 4x. What number do they both have in common? Yeah, if you said 12, that's correct. So what number do we have to multiply the first line by to make -3x become -12x? Yeah, you're right. It's a 4. We're going to go ahead and distribute that to all terms inside the equation. So we've now changed it to 4y minus 12x equals -52. Okay. What number do we have to multiply this second equation by so that plus 4x would turn into a 12x? Yeah, you're right. It's the number 3. And we're going to distribute that 3 to every number inside the equation. And we end up 15y plus 12x equals 33. Okay. So what we have done is we have manipulated both equations so that our x terms, because we decided to get rid of x first, I could have done this with y instead, but our x terms are opposites. The reason this is an awesome thing is we are going to add these two equations together. Yep, we are allowed to add equations together. So we're going to add these two equations together. What is 4y plus 15y? Again, we're adding our like terms together. You get 19y. Negative 12x plus 12x, that's the number 0. Oh, look which variable got eliminated. And negative 52 plus positive 33, that's going to be a negative number. And then we're going to need to borrow. We get a 9, and we get negative 19 there. Now I'm going to shift to the right page here, but 19y plus 0 is really just 19y equal to negative 19. So when we created opposites on each other, we eliminated a variable. And what that does is makes a simple equation for us to solve. This one-step equation will help us figure out that y equals negative 1. Now, when we have to find the x value, because the answer to a system of equation is when the two lines intersect on a coordinate plane, which is an ordered pair, we substitute this y value we found into either equation. Doesn't matter which one we use. That's the better part about this problem, or this strategy of elimination versus substitution. It doesn't matter which one you use. So I'm going to choose the easier looking one in my mind, which was the first one. It just looks easier. So I write that down, and we substitute in for the y value a negative 1 that we found. And now we're going to solve for the x value. We have no distributive property. There aren't any like terms. There is an additive inverse. The additive inverse of negative 1 is plus 1. And then to get the x by itself, we use its multiplicative inverse. And we find x equals 4. I tried to use the same system as the substitution method, so you are able to at least compare which one you liked better. So, as you would expect, the answer to this problem, which we already knew from the other problem, was 4, negative 1. So the last part of this note, because it's gotten really long, I'm just going to show you the last two parts of our slides here. We're going to skip that word problem, actually. And can you please copy down here what you see? This will be the end of our video lecture, and we'll discuss the rest of this in class. So again, go ahead and copy these two last examples down, the no solution and the infinite solution example on your notes. If you have any questions, list them in the question column, and thank you again for participating in another video lecture with Mr. Connect.